for joining us this week for a seminar given by Dr. Carrie Lebowski. Dr. Lebowski was raised on her family's farm in Lake Winola, Pennsylvania. She earned a BS in soil science from Penn State University and went on to earn both her master's and PhD in soil science from the University of Minnesota. Dr. Lebowski is now a professor of soil science and a soil fertility nutrient management extension specialist for University of Wisconsin-Madison. Her applied research elucidates the biogeochemistry and subsequent best management practices to reduce nutrient losses to the environment and improve nutrient use efficiency of nitrogen. Using research data, she develops soil fertility recommendations and tools to assist farmers and agronomists in making nutrient management decisions that support economically and environmentally sustainable grain and forage crop production in systems in Wisconsin and the upper Midwest. She also routinely works with state and federal agencies as they develop nutrient management standards and regulations. Please help me welcome Dr. Carrie Lebowski.
All right, good afternoon, everyone, and I'd just like to thank the graduate students for inviting me. It's a pleasure to come to Iowa and talk about nitrogen and corn, right? You got to be a rock star if you're here doing that. So the title of the presentation today is Assessing the Value of In-Season Nitrogen Application for Sustainable Midwestern Corn Production. And you say, well, you know, why are we still talking about time of nitrogen application, right? We've been studying this for decades along with rate. And they form, two of the 4 R's for nutrient stewardship: the right rate, the right source, and the right time and place. But why we're kind of interested in timing still is the results aren't always consistent. So the consistencies we have are if you've got sandy soils, in-season applications, we know you got to do those. There's just too much early season loss. But when we start looking at our medium and fine textured soils, depending on the study and the site conditions and even the weather in those particular years, it's not always very clear that side dressing or in-season or split applications are always superior to pre-plant or at-plant applications. And what's important about that is I think many of us know that that's not true because we've looked at the literature and conducted some of the studies, but there's been a big push recently, whether it's NGOs, agency staff, to say that all growers all the time should be applying nitrogen in season. That's going to be how we're going to help fix our problem with nitrogen loss to water. I'm not talking at all about gases, so don't ask me. We didn't measure them. We're just going to talk about water and potential losses. So there's that push that's what we should be doing. But is it really profitable to do that? That's what we want to evaluate that. And should we be making that recommendation carte blanche? Everybody should do this all the time. And so that's kind of the premise of this. The study, before we get any further, I need to acknowledge a whole lot of people. So first I've listed here Chris Bandura. He's was my graduate student. He was a master's student that finished in June. And so this was his thesis. And then I also need to acknowledge our larger project team. Because when we talk about the Midwest, it's a big area, and this was a big project with a lot of people involved. We had funding from DuPont Pioneer. Paul Carter and John Shanahan pulled together this team. You can see the PIs that we had throughout the Midwest. John Sawyer was the PI here from Iowa. This project was really neat because some of these folks I've worked with before and knew fairly well, and others I really didn't know very much about at all. So it's been a neat process of getting together and learning and thought. And so with that, we're going to get into this a little bit more. The objectives that Chris and I were looking at is we wanted to evaluate the effect of N application timing on the potential for nitrogen loss as measured by residual soil nitrate. I want to be clear here, we're only going to be talking about potentials. We didn't actually measure N loss in tile or groundwater or lysimeters or anything like that. It's just the potential via residual soil nitrate. We want to look at the economic optimum N rate and profitability, because if farmers aren't profitable, we're not going to have farmers. And then the next point we wanted to look at, objective, was to determine if nitrogen use efficiency, if any measure of NUE, can be useful for assessing the balance between the economics and environmental component of nitrogen fertilization. Can it be used as a tool to pinpoint, you're doing a good job or you're not doing a good job? So with that, our research sites, this study occurred in 2014 through 16. Each state had a pair of sites each year, and they tended to move around. It was not the same piece of ground every year, so it might have been, in some states, it might have been the same research farm, but it was a different piece of ground. So you can see the broad geography that we had here. The different symbols represent the different years of the study. Nebraska and in Minnesota, the blue represents where we had irrigated sites, and those tended to be sandier sites. The red symbols here in Iowa and North Dakota, I've got a few others, those are tile drain sites. And so you can see that we had some tiling, but not exclusive tiling. Within the sites selected, predominantly it was corn following soybean. We did have 5 sites where the previous crop was corn, and one, a North Dakota site where the previous crop was sunflower. There was no recent manure history on these fields, so that's not an immediate thing that would be changing up our end response. And the tillage varied. We had no-till, and then we had various forms of reduced tillage. We followed a standardized protocol, which I'll get into in a minute. And that standardized protocol is really powerful because there are times when we're looking at research studies we've done, and John Sawyer and I talk, and he has a study and I have a study, and we might have some things that are really similar to what we're doing, but they're not identical. We may not be collecting the exact same pieces of information, or some other things a little different. And so we had this standardized protocol. I also want to point out these 2 sites per year. Each PI selected them, and the idea was to have some different levels of productivity, something that would be considered a highly productive site, and then something that would be considered less productive, not necessarily poor productivity, but just not as high. To give you an idea of what we were looking at, here's a textural triangle with all of the locations plotted, so you can see the range in textures that we had out there. Here's the range of soil organic matter content within the study. So we had, 10 to 4.8 grams per kilogram, and our drainage classes varied. We went from poorly drained to excessively drained, and I want to point out that not all of the poorly and somewhat poorly drained sites were tiled. Some were, and some weren't, and that factors into some of this data, and I think broadly as we look into other things, not just here today, but the bigger picture of the study. And so getting into our treatments that we had at-plant applications, so you'll see that abbreviated as AP, 0 to 314 kilos per hectare in 45 kilo per hectare increments. Then we had a split application that was 45 pounds at plant, and the remaining occurred at about V9. And so that was also in 45 kilo per hectare increments. All nitrogen was broadcast as ammonium nitrate, and we had a randomized complete block design. We specifically chose ammonium nitrate, and we took a while to decide on that. It wasn't a slam dunk. We had some discussion about it, and we wanted to have a form of nitrogen that we weren't going to be losing. Wouldn't be a volatilization loss, so we can focus on what the nitrogen's actually doing in the ground system without worrying about volatilization and other issues. And also with the broadcasting, it meant that we didn't have to worry about who had, maybe John's got some equipment that I don't have, and that factors into the study. Everybody can do the same thing with a bucket full of fertilizer and spreading it out. Some key measurements for what I'm going to be talking about today. These are by no means all the measurements, because there were a lot of measurements taken on this plot. We have above ground biomass at R6, along with the total N uptake, grain yield and total N uptake, or removal in grain, post-harvest soil nitrate. So that's after harvest, 0 to 0.9 meter profile in 0.3 meter increments is what was sampled, and soil nitrate was measured, and every site had automated weather stations collecting data. And so those are just the pieces we're using today. And here you can see this is a ridge top in southwest Wisconsin. Beautiful view from there. And I think just on the beyond the edge there was the Mississippi River. We couldn't quite see it. So this would be in the driftless area, which would be very similar if you cross that river and what Iowa looks like up there. So first part, we'll focus on the potential for N loss. So just get everybody up to speed on a few things that we'll be talking about. So here's some of our yield response to nitrogen curves. We have our N application rate versus yield and our two different application timings here. To calculate the economic optimum N rate, which is EONR, we used a nitrogen to corn price ratio of 5.5. And so to put that in English units so you can think about that, that's like 40 cents per pound of N and $4 per bushel of corn. Now the other thing we want to know about with those EONRs, but it's hard to get at, is what's the variation? Is this EONR of 102 different than 77? And the statistics on that are not easy or clean. So we went for a practical approach and said, let's look at $2.50 per hectare profitability. And that's $1 per acre. And we said, what are the N rates within that range of profitability that produce the same profitability as the EONR? And one of the reasons we use that is the states in this study that use the maximum return to nitrogen philosophy for corn N rate guidelines, Iowa is one, Wisconsin's one. We use that $1 per acre in part of our recommendations that way. And so here you can see the pale blue versus pale pink. They're two distinct lines or regions. So we said at this particular site, we consider the EONR at plant and the split to be different from each other. The other thing I want to point out here that we'll use more in a few slides is the average width or range of N rates here, if we think about that width there, was 20 kilograms per hectare, so across all 49 sites. And we're going to use that 20 kilos per hectare for some other groupings of things. So let's look at some of our data here. This is our relationship between delta N and residual soil nitrate. And I really wish Dr. Malorino was here because he loves to splatter all kinds of data on his slides. And I still don't think I have more points than he puts on some of his, even though there's a lot of N rates here and a lot of sites. So here we've got delta N applied, okay? And what this is it's the N rate applied at a site on a treatment minus the EONR for that site, okay? So it's a way to normalize the data because the EONRs for all the sites was all over the place. So we're normalizing that data, and this is the residual profile nitrate, or RSN. We have the circles are the at plant, and the triangles are the split. And you can see we've got two lines here representing that data. And if we look at the estimated residual soil nitrate at the zero, which is EONR, we have 20 kilograms of N per hectare more residual nitrate with a split application compared to the at plant, okay? So splitting leaves more N behind. Not necessarily surprising, other studies have found it, but no other studies have had this kind of power with this many data points to really be able to look at a full curve with that. And so we saw some things when we first plotted this, because first we did this in just all black points kind of thing. And we said, what's going on? Who are these guys up here? Well, who do you think these points are? That's Iowa. One of the Iowa sites. There's just incredible residual soil nitrate there. And so we started saying, well, we gotta sort out some of these things a little bit here. So that's why we got some colors on here. So the first grouping we pulled out is we knew we had sites where there was no response to N. It didn't matter how much we put on, we didn't get any more yield. Or there were sites that had a minimal response. That would be 40, there was just a little bump up to the 45 kilo per hectare rate, but then nothing else, so it's just tiny. So those are yellow, and they all show up with essentially high residual soil nitrate, and that makes sense. And then we said, okay, that didn't get at whatever this was here. And so we started digging around in the data a little bit more. Well, this is a tiled site. So we said, okay, what about all of the tiled sites? What's up with them? So the orange represents tiled responsive sites because there was one tiled site that is in the yellow grouping that was non-responsive. And then we also noticed in looking at the data in a tabular fashion that there were some sites that just didn't seem to have very much residual nitrate accumulation at all. It was pretty darn low, even at the highest N rates. So we started pulling those out, and those are all these magenta points down here. And those are essentially situations where you had high nitrogen loss. Sandy soils with lots of rainfall, at plant applications. That's what's showing up down there. There's a site in there, a Missouri site that had, apparently there was a dike not too far away on the other side, and the water level in the river was pretty high, and so the water table in the field was pretty high. There wasn't necessarily a lot of standing water in the field, but the water table was high. So there's things like that where we had high or minimal accumulation of residual soil nitrate, which is pretty much high N loss situations. So say, okay, well, what do we know about those individual groupings, and can we learn more? Is it just that one Iowa site that's causing this to be, 20 kilos more? It'd be nice to just blame Iowa for one thing, right? So we looked at this a little bit more, and we saw that at individual sites, the residual soil nitrate for split was significantly greater than at plant at 6 tiled and responsive sites and 2 sites that we put into the all other category. But that wasn't all tiled and responsive sites, because there were 7 of those. So there was one that it didn't make a difference. Then we had one site where there was a significant difference between these, and there the at plant had higher residual soil nitrate. And that was a site in Missouri, and we still don't have a good reason why. We've talked with Newell Kitchen several times about this site, and it'll just be one of those mysteries of life, I think. But so it's not always that the split application had high residual soil nitrate. One time the at plant did, and so there was all total 8 sites that say pulled the curves up and one that pulled it down. But when you look at all of that data together, in general, split leaves behind more nitrogen. So then the question is, well, where's the nitrogen going for the at plant, if it's not left behind? Is it being taken up more by the crop, or is it being lost? So we started looking at total N uptake. And we've got all that same data again, delta N versus total N uptake. And there's no significant difference, no matter when you put it on. At the E1R right here, timing doesn't matter. The crop still took up the same amount. Okay, so that says, that means, it's probably loss that's happening if the crop's taking up enough. And so we decided to look at that a little bit more in depth and look at apparent unrecovered nitrogen, okay? And so apparent unrecovered nitrogen, if you focus over here, I've got the calculation of that. That is the N application rate of a particular plot minus the fertilizer-derived N uptake, and then subtracting off the fertilizer-derived residual soil nitrate. And by fertilizer-derived, I mean the difference in N uptake or residual nitrate of that plot or treatment, and subtracting off what we found in the check plot. Because the check plots produced yield, right? And so they took up nitrogen, and so we shouldn't be falsely trying to count that nitrogen. And the check plots also lost nitrogen. I should point that out back here. Down here, look how these delta N's are really low. There's check plots down in here, and they're still losing N. Even if you didn't put any on, we still are leaking out of the system. And so we're correcting for that. So we're only looking at the N we applied, how much can we recover? And so we're saying what's apparent unrecovered. And in looking at this, we can find that apparent N recovered was 25 kilograms of N per hectare greater for the at plant compared to the split. And I thought, well, that's nice because stuff's adding up. You know, if we had, for residual soil nitrate, for the split timing, we had 20 kilos more left behind. And if we look at apparent unrecovered, for the at plant timing, we've got 25 kilos that we can't account for more than the split application. So it's saying that, you know, at the economic optimum N rate, it's not if nitrogen's going to be lost, it's when it's going to be lost. Are you going to lose it early in the season, or do you have the potential to lose it after the season's over? You know, and we didn't measure that. We didn't come back later on to determine how much was lost over winter or anything like that. So it's not a matter of if, it's a matter of when. And this is contrary to what you know, some folks out there would like to believe, that keep wanting to push in-season applications as the cure-all for our nitrate troubles. It's not going to help if we're fertilizing for EO&R. So this comes back to, you know, timing is important, clearly on sandy soils. You don't want to be putting on early, but rate is still a big driver. Too much is too much. And we got to figure out how to get at the economic optimum N rate. So my next question then is, how high does nitrogen applications have to be before the residual soil nitrate starts to increase substantially? So we saw that curve go up, but there's just so many points there. How can we like get a handle on it? And so these box and whisker plots were designed to try and get a handle on it. We've got the at plant on the left, the split is on the right. And we've got categories. We kind of sliced up that graph previously. And if we look at the center here, we've got -10 to 10. And these are delta N categories. And so the EO&R was encompassed in this -10 to 10 kilos per hectare. I said, why did you pick that? Well, remember I said when we looked at that, the range of N rates within $2.50 per hectare of the EO&R was about a 20 kilo per hectare range. So that's what we did. -10 to +10 is a 20 kilo per hectare range. And so then we just kept chunking them up like that. And so we've got all of our mean separations here, and it's hard to see those, so we've got them colored a little bit. Just want to put my little money bags there at the EO&R so you can see that better. So let's look at the category that includes 0 delta N. So that's the EO&R. Let's look at, oops, gotta go the right direction. Here we have all of the N rates that had the same letter as the A. So there was an A on all of those. So if you put on the economic optimum N rate, you were statistically had residual nitrate that was the same as not putting any N on at all. And if you put on the economic optimum N rate, you had residual soil nitrate that was not significantly different than if you put on for split applications up to 70 pounds over application, and for at plant also up to 70 pounds over application. So you start saying, well, you know, if you start saying how much is too much, well, this is really 70 pounds over applications, kind of getting big, and you could see this is really going up. And so we started looking at this more, and I'm presenting this really, you know, quick to you. You know, we spent, you know, days just kind of looking at graphs and